Guys, and welcome to the Academic Chemistry Notes. We are in Unit 1, Topic 6, which is significant figures, and today we're going to talk about what significant figures are and how they relate to taking measurements. Because that's the most important thing in chemistry, is being able to go to a lab and do something and then making sure it's able to be reproduced exactly the same way by another scientist. And to do that, we need to have a way of documenting which instruments we're using so someone else can do the exact same experiment. For these notes, if you are following along in my follow-along notes, you're going to need a highlighter, so please make sure you have that. So, when you are taking measurements, there's a few rules, and the first one is you always have to have a unit, the correct unit after your measurement. If you don't have a unit, you don't know what you're measuring. So you could write on a lab report, I have 3. And I'll say, what, 3 bananas? No, you need to say I have 3 meters, 3 grams, 3 milliliters, whatever it happens to be. So do not have any naked numbers. Those are numbers without units. They are totally inappropriate in chemistry, and you won't get any credit if you give me an answer with a naked number. The next rule is if you're looking at a liquid, you're measuring the volume, you're going to look to the bottom of what's called a meniscus. So if you look here, see how the liquid actually dips like this? This dip is called a meniscus, and you look to the bottom of it to figure out what your measurement is. The reason for that is liquids may be attracted to the glass of the measuring device. So if you see here on the sides, you'll see it's a little bit higher. And that's because the glass actually pulls it up through capillary action. So it seems to be higher, but you don't actually have that volume. That's just an attraction to the glass. So you want to look to the bottom to ignore that attraction that's throwing off your number. You also want to look at eye level. So that means that when you are in the lab, you are going to have to bend over a bit so you really look right at eye level. If you look from above, then you're not going to get a proper measurement. So when you are measuring, you bring your eye down. Now obviously this eye would have goggles on it in the lab, but make sure you are looking right at eye level and you're looking at the bottom of the meniscus. The last rule for taking correct measurements is always use the right number of significant figures for the device. You're probably like, what the heck are significant figures? Or you're thinking, oh my god, I've heard someone talk about significant figures from a previous chem class and said it was scary. It's not going to be scary. We're going to break you through all of the topics, just break it down a little bit and go through it one by one. So, significant figures, otherwise known as sig figs if you're in the business, that's like the cool, hip chemistry way of saying it. You could also say significant digits because a figure is a digit, so it's just saying a single written number. Are the important non-placeholder numbers in a measurement that allow the user to evaluate the precision of the device. There are 2 parts to this statement. The first part, that they are important non-placeholder numbers. So the first part is identifying which numbers are significant. We're going to go through that. The second part is evaluating the precision of the device. We're going to explain how the sig figs can tell you how precise that measuring item is that you used in the lab. So let's start with sig figs are important non-placeholder numbers in a measurement. All right, so we're going to go back right now to metric conversions, which we've already done. So this measurement, 0.072 meters, we can all agree that this is a meter stick. And it would be about this big, right? It is just under a tenth, so it is just over 7, a little bit more here. So if I put in my centimeters now, measurements, I can clearly see that this is 7.2 centimeters. These are the exact same measurement. I didn't change the size of this red block, but if you notice, this looks a little different because of my prefix. So I have a question for you. Were the zeros at the beginning of 0.072 meters important? Do I have to have them written in my measurement? Are they that important? And the answer is no, because I can add a prefix, and the prefix takes the place of those zeros. Those zeros are what we call placeholder numbers. They're just telling you how big or how small the number is, but I can also do that with prefixes, so therefore those zeros are not important or they're not significant. See where I'm making the connections now? So let's go through the rules of what makes a number significant when looking at it so you can quickly look and identify, oh, that digit's significant or it's not. So how to evaluate a measurement, which digits are significant. So the first rule of how you look at it is you start on the left, the furthest left digit. which makes sense because we read from left to right? So you're going to start on the left-hand side. Nothing significant until the first non-zero. 1, 2, 3, 4, 5, 6, 7, 8, or 9. Everything is significant until the end of the number from then on, unless it's a 0 at the end of a whole number without a decimal. Okay? If we are in scientific notation, everything in the coefficient is significant. So now let's take these rules, let's go through a few measurements, and let's determine which digits within that measurement are significant. So we are going to use the rules that we just established and go through each of these measurements. So the first one, 0.000089 liters. So you start on the left, and the first significant digit is the first non-zero. These are all zeros, they're not significant. So the first thing is going to be the 8. Then everything else in the number is significant unless it's a 0 at the end of a whole number. Well, this isn't a whole number. Whole numbers are 1, 2, 3, 4. There can't be any numbers after the decimal. So that means the 9 is significant too. So we have two sig figs. The 8 and the 9 are both significant in this measurement. Let's do this one. Start on the left, the first non-zero. Well, we start off with a non-zero. And then everything else is significant unless it's a 0 at the end of a whole number. Well, since I have this decimal, it's not a whole number. So that means everything else is significant. All of the digits in this measurement are important. They cannot be chopped off or replaced with a prefix. 850. The first digit is our first sig fig. And then everything else is significant unless it's a 0 at the end of a whole number. This 0 is at the end of a whole number. Notice there's no decimal, so it's like our counting numbers. So that 0 is not significant, but the 5 still is. So the 8 and the 5 are significant. In this, we have 4.80 times 10 to the 23rd. This is in scientific notation. So when it's in scientific notation, anything in the coefficient is significant. So all of those digits in this coefficient are significant. The 10 to the 23rd is just a placeholder, so it's telling you how big or how small. You could replace this with a prefix that means 10 to the 23rd. 300 with a decimal. Notice that decimal. So initially, you might think that just the 3 is significant. The 3 is the first non-zero, and then there's zeros at the end of a whole number. But if there's a decimal at the end of that whole number, the reader's saying, hey, that last 0 is also significant, so I need to include it. So the decimal is almost like this magic button that says, go ahead and include everything at the end as being significant. So both those zeros get to count as being significant. So all of these measurements, anything I've highlighted is a significant figure or a sig fig, meaning they have to stay within our measurement. They cannot be replaced with a prefix. They are important to tell your reader what exactly was measured. All right, the second part of that statement was sig figs in a measurement allow the user to evaluate the precision of the device. So this is the same bug. I think it's a fly. I'm not a bug person though. And if you look at it, it's going to be obviously the same length. It's not like the bug changed, but 0.6 centimeters here and 0.628. This last measurement is clearly much more precise. It's much more spot on. And if you look at your measuring device, this is clearly much more precise. There's much more information here because there's more graduations versus my first one. So the more graduations, the more smaller sig figs you can include. So the last significant figure is always estimated. So let's look at this. I know where my 0 centimeters is and my 1 centimeters is, but the 6 here, I don't really know. I estimated or I guessed, I kind of eyeballed it, is another way of saying that. So this 6 was estimated. Versus here, I know that 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, I know that 0.6. So I estimated the 2 here. Here, it's kind of harder to see, but I know exactly right here, right below it, is 6.62. So the 8 was estimated. So you can see the last digit is always estimated. The second from last digit tells the reader how calibrated the graduations on the measuring device were. So let's look at this digit. Our 2 was estimated because that's the last sig fig. So that means our 6th position is in the 10th position, and that's where my graduations are. And you can see I have 10th 2/10, 3/10, 4/10. These are all a tenth apart. To be sure to use the right number of sig figs. So here's what you're going to do when you're taking a measurement. First, analyze the smallest change in graduations. Write the last number the measurement passes on your graduations, those are those tick marks, and then estimate one more digit. So let's do some practice. So you see this, bringing up our number line here, all right? So you can see that the graduations change by the ones position. This is 1, 2, 3, 4, 5, 6, etc. So if I'm looking at the bottom of the meniscus, I know it passes 21. It doesn't get to 22, so I have to write 21 as my first data point, or my known data. I know that I have 21 milliliters. Then I need to estimate how much in between it is 21 and 22. I'm going to say that bottom is about 0.6. But since it's estimated, we might have different numbers. Like you might have said, oh, that's a 0.8 or a 0.7, and that's okay because the last digit is estimated. It's not exact. And that's going back to this. Our last digit is estimated. The more calibrated the device, the more precise your measurement's going to be. All right, so I want you to take the measurement of this piece of stone that we are measuring in centimeters. So freeze the video, come up with what you think, and then I'll show you some correct answers. All right, so you should have gotten an answer for this, and here are ones that I am going to say are okay. You could have 1.36, 1.37, or 1.38. They all have to have centimeters. Did you remember the unit? The reason is this is passing 1.3, so you have to have 1.3. And then you have to tell your reader how much between 1.3 and 1.4 it is, so you have to have that second position, the 6, the 7, or the 8. Let's do another one. All right, what do you think the volume of this is in milliliters? So freeze your video, write your answer, and then I'll have some answers for you. All right, so I hope you looked at the bottom of the meniscus, and it looks exactly like it's at 24. So I would put 24.0. Remember, you're changing here by 1. So this is 21, 22, 23, 24. So if you think it's right on 24, then your estimated digit has to be a 0. So don't forget to put that last estimated digit. Otherwise, you're saying that you don't have ones on the device. It's changing by tens, and that's not true. So make sure you put in your estimated device even when it's right on that graduation. All right, good luck with this section. Make sure you ask me if you have questions, and I'll see you in the next set of notes.